SwayamPrabha. Digital India. Educated India.
So, I hope this first example is clear, okay, pretty simple, right. So, now let us go and do another example, okay. So, let us say we do a second example. So, since I could stabilize with a proportional controller itself, we stop here, that is it, okay. So, I am not even trying other controllers, right. So, of course, one could try them, okay, but we are just stopping here, okay. So, let us say as a second example, let us say we want to choose the plant transfer function as s squared plus 1, right. So, is this plant stable? So, what is the order of this plant? Second order, right. So, is it bounded input, bounded output stable? No, right. So, as I told you, we'll introduce another notion of stability called stability in the sense of Liopanov. It will so turn out that as per that notion of stability, this is stable in the sense of Liopanov, okay, as long as I have simple roots on the imaginary axis. But we have already seen that here the poles are at plus or minus j. If I have non-repeating or what we call as simple poles, right, on the imaginary axis, like what will happen is that like if I provide a sinusoidal input whose angular frequency is equal to the magnitude of the pole, the corresponding output essentially goes to infinity in magnitude, right, as time progresses. So, we see that if to the system, if you provide cos t or sin t, the output essentially blows off, right, to infinity, okay. So, this is Bibo unstable, okay, and of course, like some people will call it as marginally or critically stable, okay. So, it depends on which school of thought you belong to, right. So, essentially, okay, so that is it, okay. So, that is what we have here, right. So, now once again, like we want to stabilize, like say, yeah, one may call it marginally critically stable, but I do not think, like any one of us want to have this as a transfer function of a practical system, okay, for multiple reasons, okay. First reason is the following, right. Let us say, just to give an example, let us say we have an automotive suspension, right, whose transfer function is like this, okay. Would that car even sell? Can you sell that car? Imagine that you have an automotive suspension, whose transfer function is this, right? And suppose I drive that car on a road whose frequency is at a speed such that like the road input which comes into the car from the tires, like has an angular frequency of 1 radians per second. Let's say I excite that. I can always do that, right? Suppose if I excite it, what is going to happen? The car is going to essentially vibrate by a huge amount, right? So, I won't even buy that car, right? So, because that is going to be very, very uncomfortable, okay. Second thing is, please note that, like all this analysis is only approximate. So, if I say that the poles are at plus or minus j, okay, that is only an approximation, okay. In reality, like the poles can be in a region around plus j and minus j. So, it can just because the system parameters may vary, like whatever I have done is an approximation, right. So, essentially I might have not taken into account some dynamics. So, there may be unmodeled dynamics, there may be uncertain parametric uncertainties and so on, right. So, the poles may be around a region, okay, of plus or minus j. So depending on my luck, like sometimes it can be in the right of plane, marginally in the right of plane, but still it's in the right of plane. The moment that happens, obviously the system becomes unstable, right? So we in practice, due to these reasons, we do not want to place any poles on the imaginary axis by design. Okay, if it comes to us naturally, if a plant naturally has poles on the imaginary axis, we stabilize by using closed loop feedback. Okay, that's what we are going to do. Okay, and even we will talk about what is called relative stability later on, right? Even we don't want the poles to be, for this reason, we don't want the poles to be very close to the imaginary axis. Why? Because once again, let's say I place poles, which are very, very close to the imaginary axis, right? Once again, this pole may be in a domain or region around the whatever I have specified as one particular location. So we don't want it to be too close, okay, within quotes to the imaginary axis, right? So what we call as relative stability would be used to quantify those effects. Okay, we'll come there. Okay, so obviously we don't want essentially poles on the imaginary axis, like from a practical perspective. So what we do is the following. We once again stabilize, right? So let's say I am drawing this block diagrams now. Okay, in future you should be able to visualize, right? So for a few examples I am drawing this block diagram. Okay, so we are considering unity negative feedback. So this is the diagram. So we have E of S and we have the controller transfer function C of S, right? So once again we start with proportional control. Okay, Kp, right? So this implies that G of S is going to be equal to C of S times P of S, right? Okay, and that's going to be equal to Kp divided by S square plus 1. So the closed loop transfer function is equal to G of S divided by 1 plus G of S H of S. That's going to be equal to Kp divided by S square plus 1, the whole thing divided by 1 plus Kp divided by S square plus 1. So if I simplify this, what will I get? I will get Kp divided by S square plus Kp plus 1. Okay, that's what will happen. Now what will be my closed loop characteristic equation? Of course I'm using all these abbreviations. C dot L means closed loop, CHAR means characteristic, EQN dot means equation. Okay, so what will be the closed loop characteristic equation? It will be S square plus Kp plus 1 equals 0. Okay, now what can you tell about the closed loop poles? So this is a quadratic equation, right? There are going to be two closed loop poles, two roots, right, to this equation, right? Where are the two roots? So of course in this case I can write it in a very simple way. So I can say this is going to be square root of minus Kp plus 1, right? Am I correct? Is it right? So if Kp is if Kp plus 1 is negative, right? So we see that we can have two cases. Let's say if Kp is greater than minus 1, right, what's going to happen? Kp plus 1 is going to be positive. Then what are we going to have? Closed loop poles on the imaginary axis. I hope all of us agree, right? So if Kp is greater than minus 1, we have closed loop poles on the j omega axis. Is that desirable? No, right? Because we want closed loop poles in the left half complex plane, right? So if Kp is equal to 1, what will happen? Sorry, equal to minus 1? Closed loop poles at 0 and 0, okay, even worse, right? Because we know that if you have repeated poles on the j omega axis, it's the output is unbounded for any bounded input. Okay, that is already known. And what happens if Kp is less than minus 1? We will say that one closed loop pole each on the negative real axis and positive real axis, correct? Okay, I hope you agree, right? That's what will happen, and Kp is less than minus 1, right? So, either see, irrespective of what range of Kp we choose, like between minus infinity and plus infinity, is there any value of Kp that will essentially achieve closed loop stability for this system? No. So, this implies that proportional control would not work, would not achieve closed loop stability for this plant. Okay, and the way we have done closed loop for this plant with unity negative feedback. Okay, that's important, right? So, because that's what we have done, right? So, okay, so I'm writing it once. Okay, in future I will just say it doesn't work. That's it, right? So, but then I want to write very carefully, right? So, for this particular plant, and when we do unity negative feedback, the proportional controller would not stabilize the closed loop system. Okay, that is the conclusion we need to draw, right, from this example. Then what can we do? Now I go and try, maybe, what can I try? I can try Pi, for example, right? So, let us say we try Pi. So, that means that we are going to have the controller transfer function to be Kp plus Ki by S. This can be rewritten as Kps plus Ki the whole divided by S. So, this implies that G of S, which is C of S times P of S, is going to be equal to Kps plus Ki divided by S times S squared plus 1, right? So, this will give me Kps plus Ki divided by S cube plus S. Okay. So, as a result, the closed loop transfer function is going to be equal to G of S divided by 1 plus G of S H of S. This is going to be equal to Kps plus Ki divided by S cube plus S, the whole thing divided by 1 plus Kps plus Ki divided by S cube plus S. Okay. This is going to be equal to then Kps plus Ki whole thing divided by S cube plus Kp plus 1 S plus Ki. Okay. So, as a result, the closed loop characteristic equation is going to be equal to S cube plus Kp plus 1 S plus Ki is equal to 0. Okay, that is going to be the closed loop characteristic equation, right? Okay. Now, what can I say about the closed loop poles? Of course, now you see that the closed loop system is of order 3, right? See, the order of the closed loop system is the order of the denominator polynomial of the closed loop transfer function, right? So, that can keep on changing. See, the plant may be the same, the plant may be a second order plant, but once we introduce a controller, we are introducing its own dynamics, right? So consequently, the order of the closed loop system can change with the controller. So here we have obtained a third order closed loop system. When we tried with the proportional controller, the closed loop system was still order 2. Okay, now it has become order 3. So obviously there are going to be 3 roots, right? 3 closed loop poles. Where are they? So you can see that the problem becomes, as you keep on going ahead, things are becoming more challenging, right? Isn't it? Okay. So in fact, we started off the premise that, oh, we don't want to work with ODEs, let's apply Laplace transform and work with algebraic equations. Okay. Even algebraic equations have their own challenges. Okay. So it's not that just because we have gone to polynomials, like things become very straightforward. Yes, it's easier to do by hand. Okay, but still, we need to learn some theory. Okay, so I'm going to digress here and teach you some general theory, and then we'll come back to this. Okay, so now you will understand that how mathematics can be used for practical design applications. Okay, so let's go learn some general polynomial theory, which leads to what is called as the Routh's criteria, and then we'll see how it is used for control design. Okay, so that's something which we are going to look at. So I am pausing the example here. We'll come back to this, right, after we learn the Routh's criteria, right? So we learn, let's consider a polynomial d of s, which is written as a naught s power n plus a1 s power n minus 1 all the way till a n minus 1 s plus a n. Okay, so that's my polynomial. Okay, so a polynomial, obviously this is an nth order polynomial, right? So it will have n roots, right, if I solve it, right? So this is a definition. A polynomial is said to be Hurwitz if all its roots have negative real paths. Okay, that's when a polynomial is said to be a Hurwitz polynomial. Okay, so in other words, if I have a nth order polynomial, all n roots must be in the left of complex plane, right? Then that polynomial is said to be Hurwitz. Okay, of course we are considering of course in this particular field, for our particular application, we consider only real polynomials. That means that all coefficients are real numbers. A naught through an are real numbers, for us. Okay, that means that if I have a complex root, the conjugate also must be a root. Okay, so please remember that. Okay, so how is this related to our control design? See, we want all closed loop poles to be in the left of plane for closed loop stability, right? We have figured it out from basically our derivations, right, previously, how we correlated the physics behind Bibot stability to the mathematics. So now how do I get the closed loop poles? By solving for the roots of the closed loop characteristic polynomial, which was 1 plus g of s h of s, right? The denominator polynomial of the closed loop transfer function is the closed loop characteristic polynomial. Okay, so if I ensure that my closed loop characteristic polynomial is Hurwitz, I am done, right? I ensure that the closed loop system is stable. Do you agree? Okay, so let me repeat it, right? 1 plus g of s h of s is the closed loop characteristic polynomial, right? If I ensure that my closed loop characteristic polynomial, which is the denominator polynomial of the closed loop transfer function, is Hurwitz, then by the definition of what is said to be a Hurwitz polynomial, the all the roots of the Hurwitz, that is closed loop characteristic polynomial, will be in the negative, left of complex plane. So which means that my closed loop system is going to be Bibot stable. Done, right? Okay. So our task now boils down to figuring out the values of the proportional integral derivative gains as they may appear in the closed loop characteristic polynomial, like here, right? In this closed loop characteristic polynomial, s cube plus kp plus 1s plus ki, you can see all the controller parameters appearing. Now we ask the question, when or for what values of these controller parameters, if they exist, okay, would the closed loop characteristic polynomial be Hurwitz? Okay. So that is the question we are going to answer in general in the next class. Okay. So we are going to stop with this question. Okay. How do we evaluate whether a polynomial d of s is Hurwitz?
Is it all coefficients should be positive?
Okay, I think I will leave you with this question once again. I partially have given you the answer. So, very good point, right? So, I'll just take 1 minute of your time. Sorry about that, right? So, let's say in this example, hey, why should I even do closed loop, design, right? Let's say I have 1 by s minus 1, okay? What you do is that you just do an open loop control design and then multiply by s minus 1 by s plus 1, which is a proper transfer function, and that's about it, right? So you have y of s by r of s to be equal to s minus 1 divided by s plus 1 multiplied by 1 by s minus 1. S minus 1 cancels, I get 1 by s plus 1, I am happy, isn't it? Very simple, you know, why should I even worry about feedback and so on? But why should we not do it, right? Please think about it, okay? We'll also discuss this in the next class, right? So, partially the answer has to do with the answer which I already given you today in today's class, okay? And there are more reasons to that, okay? We'll discuss that.